Okay, we're going to do some extensions now on summing infinite series. So suppose we have, again, we're going to give a definition now for what it means to converge or diverge as a series. We've really talked about this already, but we're going to get a little more formal with it now. And that is the notion of a convergent or divergent series is do the limit of the partial sums converge to a number? Okay, we've been dealing with partial sums a lot, so now I'm just saying, formally speaking, if the limit of the partial sums converge, we say the series converges or diverges. Okay. Furthermore, we can define something called a remainder. Okay. So the remainder is if we go up, suppose the sum of the first 10 terms is a half. Okay. And suppose we know that the entire series sums up to 2. Okay. If we know that's the case, then the remainder up to the 10th term is going to be 2 minus a half is 3 halves. So what that means is that the remainder should end up going to 0 as well, okay? Because this should approach this. So just another way to look at it. All right. Let's look at some problems here. We've already looked at problems like this. This should look fairly familiar. This is what we call a geometric series. We can look at it by rewriting it as n equals 0 to infinity of 1/3 to the n. Okay, so this we can sum up. We can say, well, we know that the sum of an infinite series is going to be infinite geometric series is going to be 1 over 1 minus 1/3. So we have 1 over 2/3. This is 3 halves. Okay, so just a little review. If we do the same thing, we go 1/6 to the n. But now we're summing from 2 to infinity. We have to do a little bit more work. Basically, we can write this as, let's write this out briefly, see how this is going to look, and we'll talk about how this works. This is going to be 1/6 squared plus 1/6 cubed plus 1/6 to the 4th plus dot dot dot. Now, there's a common term here. There's 1/6 squared. 1/6 squared times 1 plus 1/6 plus. So this is 1/6 to the right. Plus 1/6 squared plus dot dot. So this can really be written as 1/6 squared times the sum from 0 to infinity of 1/6 to the n. So what we can do is we can say when we have an infinite geometric series, we can say we're going to look at the first term, 1/6 squared, times 1 over 1 minus 1/6. So times what we would get if we weren't starting at 2. So basically we take what this sum would be if we were starting at 0 and multiply it by the first term of the sequence. The series, pardon me. Okay, so what do we get? We get 1/36 times 1 over 5/6, which reduces to 1/30. Okay, so it's the first term times the sum of the geometric series. The first term is 1 over 1/6 squared times the sum of the geometric series. Let's look at this one. This is a pretty interesting one. Now, this one we're trying to figure out, does it converge, diverge, and where does it go? Well, let's take a look at this. The divergence test says that if this is going to converge, this sequence better converge to 0. So n minus 1 over n better go to 0. Does that happen? Well, if we take the limit of this as a function, remember it should go to the same place, or at least it should go, if this converges, the sequence should converge, but this converges to 1. So since this sequence does not converge to 0, this series cannot converge. This diverges. Okay, let's take a look at this next one. Now we have what looks very interesting. We've got stuff to raise to a power. So this kind of leads you to think maybe this is some kind of geometric series. Okay. And indeed, it actually is a geometric series. Let's take a look at it. We're going to try to rearrange this so that we have just one thing to a power. All right, so I'm going to rewrite it as n equals 1 to infinity of 9 squared times 9 to the negative n times 4 to the n times 4 to the 1. Okay, well, so we have a 4 and a 9 squared. I'm going to pull those out front. 9 squared times 4. In here I have 9 to the negative n. That's like 1 over 9 to the n. And 4 to the n. So this is 4 over 9 to the n. Now, this will converge as long as this number is less than 1. The absolute value of this is less than 1. It is. So this should converge to 9 squared times 4 times. This is going from 1 to infinity, not from 0 to infinity. So I'm going to do it times the first term, which is 4/9, times 1 over 1 minus 4/9. Okay? So this is 81 times 16 over 9 times 1 over 5/9. Okay, cancel that, cancel that. I get 81 times 16 for 5, whatever that is. Okay, so now that we've looked at a couple of geometric series, let's talk about something called radius of convergence. The question with radius of convergence is, for what values of x does the following sequence converge? Okay, we know this looks like it's geometric. Now notice there's an x in here. So now we're looking at a function as well. We could think of this as almost like a function of x that is a series. Now I'm not going to think about it that way just right now, but keep that in mind. We can think of it that way. So this 3 is not going to matter in some sense. So I'm going to pull it out front. Okay. We have 2x minus 1 to the n. Okay, so we have to go back and think about geometric series. And geometric series says that if I have something raised to the nth power, this something will converge, I'm going from 0 to infinity, as long as, remember, geometric says we have a r to the n equals 0 to infinity, will converge to a over 1 minus r as long as r is between -1 and +1. Okay, that's the rules for converging geometric series. So what does that mean? This is our r, okay, and r is for radius. So I'm going to have, this is going to converge to 3 over 1 minus 2x minus 1 as long as 2x minus 1 is between -1 and 1. And the question is, for what values of x does the following sequence converge? Well, it converges for these values of x. Okay? Well, here's what we're going to do. We're going to add 1 to all sides. 0, 2, x, 2. Divide all sides by 2, and we get 0. Okay. So x has to be between the values of 0 and 1, not including 0 or 1. Okay, I had to remove location. So let's look at a few more examples. Okay, so here are the three examples really we've been using to determine convergence so far. There's the geometric series. Okay, we say that when n is going from 0, okay, to infinity, r to the n, as long as r is between -1 and 1, this will converge. Okay, a harmonic series, which we can only go from 1 because we can't divide by 0, from 1 to infinity, this always diverges. Okay, so we know that this diverges, this converges for r in between -1 and 1. And the divergence test, which says that as long as, if this does not go to 0, if this sequence does not go to 0, this diverges. Remember, it doesn't, the opposite does not work. If this goes to 0, this does not necessarily converge. Here's an example, right? The harmonic series, 1 over n goes to 0, but the harmonic series diverges. Okay, so these are the 3 tests we're using so far to determine convergence or divergence. Let's look at another example here. Okay, the divergent. This is not harmonic. This is not geometric. Okay, and the divergence test doesn't hold because this does go to 0. Okay, so we have to find another way to determine the convergence or divergence of this series. So here's what we're going to do. We're going to kind of look at the way this is set up. Now we have to use something we've been talking about before, and that is partial fractions in order to break this down. Okay, 1 to infinity of. All right, so let's go ahead and look how we're going to do this here. 1 over n times n plus 1 equals a over n plus b over n plus 1. Okay, those are the factors. So we solve and we say, okay, we have 1 equals a n plus 1 plus b times n. And we solve here and we say, okay, well, if n is equal to 0, okay, then a is equal to 1. And if n is equal to negative 1, okay, n is equal to negative 1, this goes to 0, then b is equal to negative 1. Okay, so this partial fraction decomposition is going to be 1 over n minus 1 over n plus 1. Okay, you can go ahead and you can try to multiply that back out and make sure that's true. But here is our partial fraction decomposition. I'm going to move down below my partial fraction work down here. Okay, well, let's investigate this series a little bit here. It's still pretty hard to figure out what's going on because this still all goes to 0. That's fine. We still don't know what's happening. So let's take a look. Let's start with 1. If I plug in 1, I get the first term is going to be 1 minus a half. Plus the second term is going to be, if I put in a 2, a half minus a third. Plus the third term is going to be a third minus a fourth plus a fourth minus a fifth plus, if we go all the way up, we're going to get, we'll just do 1 over k minus 1 over k plus 1. Okay. Well, what's happening here? This is kind of a fascinating thing here. We have a negative a half plus a half. We have a negative a third plus a third. We have a negative fourth plus a fourth. We have a negative fifth plus. Basically, everything cancels out except the first term and the last term. Okay? So if I look at this series, and I look at what happens to this series up to a value k, n equals 1 to k of 1 over n minus 1 over n plus 1, I end up with just a 1, and then the very last term, k plus 1. Okay? So if I sum up to the kth term, okay, so this is the partial sum up to the kth term, 1 minus 1 over k plus 1. This is the sum to the kth term. And what we're saying is that wherever this sequence goes, the series goes. Okay. Well, what happens if we let k go to infinity here? If we let k go to infinity, this goes to 0. So this telescoping series ends up going simply to 1. Okay, it's a pretty cool concept. That basically all the intermediate terms cancel out, and all you're left with is the first term and the very last term, the kth plus 1 term. Okay, and as we let that go to infinity, the k plus 1 term goes to 0, so all you're left with is the first term. Every other term eventually cancels out. So this idea is what we call a telescoping series. It telescopes and the intermediate terms cancel each other out. So telescoping series is a series in which terms are systematically subtracted out by later terms in the series. Now, I wanted to use the word canceled out, but subtracted out makes more sense in this case because canceling we usually think of as being division. Okay, so any series that does this basic thing is called telescoping. Right, and we'll see some other examples of that. So basically, we're left with 4 things that we can look at when we're talking about ways to deal with series. We have the divergence test, okay, which says that if the sequence doesn't go to 0, then the series diverges. The geometric series test, which says that as long as the absolute value of r, of the radius, is less than 1, and we raise that to an n, it's going to converge. And we have a formula for that when that converges. And then finally, the telescoping series, which again is not a convergence test, but basically what it says is that we have these series where if we look at a few terms, we start to see terms cancel each other out. It doesn't have to be they cancel each other out in the next term. It might cancel each other out in the third term. Okay, but what happens is we're left with typically the first term and the last term because intermediate terms end up systematically canceling each other out. And partial sums is just a tool that we're going to use sometimes to discover whether or not we have a telescoping series. Okay, that's it. We're going to practice a lot more of these in class.